Now our data is almost ready to be used for any machine learning algorithm. But before that, we need to do one more task, which is to handle outliers. Now, if we use the data at this time without handling the outliers, then what might be the case is you might have the model that is less accurate. So in order to make your model more accurate and out of the outliers, we need to handle them. So in this video, we need to handle the outliers that we have in our data, and that is to be done right in this video. And the course is about handle the outliers. It is pretty much easy to handle the outliers. I'll show you the steps to handle the outliers now. So first of all, if you need to know what are the outliers, there will be the separate video for you to check out what is the outliers and how outliers can degrade the accuracy of your model or the efficiency of the model. So here, in order to handle the outliers, what we need to do is, first of all, let us check if any of them have outliers or not. So for that, you can also call the describe function to our data frame. If you remember, initially we made this data frame. So this is our actual data frame. Now onward we will be using this data. So this is our final data frame. After cleaning, dicing and doing everything, we got to this point where we have our complete and final data frame. Now I can use this data frame and call the describe function to it. Then what we can say is, we can see something called as a mean, median, standard deviation. All of these measures can be found. And from this, you can check if we have some outliers or not. Maybe see here, in the case of lead time, we have the mean around 104. Standard deviation is right here. And in the first quartile, we have the value of 18. And in the 50th quartile, that is a median, is around 69. And 75 quartile, or basically 75%, which is the third quartile, has the value around 161. But the maximum value is right here, which is way above than these three quartiles. See here, these three quartiles have the values and the maximum values is way off from these three quartiles. So maybe this lead time attribute has an outlier. So let us check that. There are different ways to check the outliers, but this is also one step. So I'm going to use the dist plot from the Seaborn library. So this SNS is from the Seaborn library. So using Seaborn library over here to just represent the distance plot. So I'm going to use the data frame, and here I'm going to pass lead time. So lead time is that is our column of the data frame. If I run this, then you will see a plot where we can see it is kind of positively skewed data. So it is not normally distributed. So normally distributed means, if you remember, normally distributed would have something called as a bell-shaped curve, and here we have a positively skewed data. So here, if our distribution is something like this, it is also not good. If I make it over here, if our distribution looks something like this in a bell-shaped curve, then this would be a standard normal distribution. And in the case of positively and negatively skewed, the curve would look something like this. If this is the case, something like this, it is a positively skewed. And similarly, if this is the case, this will be negatively skewed. So this is positively skewed data, this is negatively skewed data. So if you check, in our case, we have this curve which looks something like this, and it resembles to this one. So our data is positively skewed. Maybe there are some outliers, and maybe these are the outliers at the bottom of our data sets. So in order to handle the outliers, what I'm going to do is, there are several methods, but I'm going to create a function which will handle this outlier. So I'll say handle outlier, and here I'm going to pass the column that needs to be handled. So in order to handle the outlier, what I'm going to use is, I'm going to use something called as a transformation. So I'll take the column and I will replace it by just using this log transformation. Log 1 plus 1p means here 1 plus, and I'm going to pass the column that needs to be log transformed. So what does this method do? This method will perform the log transformation, log 1 plus column. So let's say in the case of column, if you give the value that is 3, then log transformation will take that value and add it to it, and it will perform the calculation and you will have some values. So in the case of positively skewed data, if you use log transformation, then the outlier will be probably handled. So that was the reason. If you see the positively skewed data, use the log transformation. If you have a negatively skewed data, you will have different transformation. Maybe you can use the exponential transformation or some polynomial transformation. But in the case of positively skewed, it normally works with the log transformation. And log basically does not work when we have the log value 0, we'll have that is undefined. So that is the reason 1 is added to it, so as to remove the possibility of having 0. Because if we have the value of columns 0 here, then 1 plus 0 will be 1. So log 1 will be 0. So in order to handle this case where the log will be undefined at the value of 0, we need to have the log 1 plus method. So that is the reason we have here log 1p. So log 1p means log 1 plus. Now this is the method we will be using to handle the outliers. So let us handle our lead time method. So handle outlier is the function, and I'm going to pass the data frame, and here I will pass, that is okay, I can directly pass, or what, I can directly pass here lead time, because the lead time will be extracted from the data frame right here. So I can directly pass lead time right here. Now if I run it, then again if I plot our lead time, then see here it has been some transformed. Now no longer it is positively skewed. It is also not a standard normal distribution, but here we have something called as a density plot, which normally looks something like over here. If you remove this part from this 0 to 1, then it would completely look like we are having the standard normal distribution. So now our lead time has been handled, and maybe while plotting, let's say if I plot by just removing the values of 0, let's say here whenever I plot the lead time, I can drop the NA values right here, drop the NA's value, and if I just run this, I have just removed this, that is parenthesis. Just look at the parenthesis where it has been closed and everything. If I run this, then you can see the plot, which is something like this, by removing NA's, because after the log transformation there might be a case that NA values will be included onto our data sets. So similarly, what I can also do is I can also perform the same tasks for the next attribute, and in our case the next attribute will be ADR. If you remember ADR, it was the rate, which will be right here somewhere, ADR attribute. So now we can see here that this is the ADR, and it also has the outlier, because we can clearly see the first quartile, second quartile, and third quartile value right here. So third quartile value is 126, and see the max value, it is way off from the third quartile. So we can also see this way that there must be an outlier. So maybe this 5400 is outlier, because most of the values are within this limit. From this minimum we can see the maximum. See here, this is the observation you can check out if you need to find if there is an outlier or not. So see here, in the 25 quartile we have something that is near to the 70 value. In the 50th quartile, or basically second quartile, or the median, is around 94. The third quartile or 75 percentile is around 126 value, and see the max here, it is way off from the 75 percentile. So there must be outlier. So I'm going to plot now distance plot for ADR, which might have outliers here. There will be this many is outlier. So this many should be removed or capped, or we can also use the log transformation if we want. So let us do the same log transformation, handle outlier. This is the same function that we have created right here, which will perform the log transformation, and I will pass ADR to it. Now it will be handled, and I can also plot again after we handle it. And you can see this has been also converted right here. So see here, ADR is near to perfect standard normal distribution. Initially it was something like this. Initially it was not this one. So initially it was something that is positively skewed, something like this. It was positively skewed. Now after we perform the log transformation, we have something that is near to standard normal distribution. Now after we perform the log transformation, there is always a chance that we get null values. So we will check if we have a null values or not. So is null dot sum. So I'm going to call dot sum to it, and let us see. So we transformed the ADR attribute, and we also transformed another attribute, but ADR has now the null values at one position. So we need to remove it, or maybe we need to impute it. If you remember, we did something called as a imputation in the previous video also. That is just having to impute or fill this NAs. But in our case, what I can do is I can simply drop the NAs values. So I'll just call drop NA. I don't want it, just drop it, and in place should be true. If you have many data, then this is also an option, like you can directly drop the NAs. If you have, that is, let's say 1000 observation, then dropping the entire row might not be good idea. But in our case, see, we have so many observations, so dropping only one row does not make any difference. So I can just drop it. Now if I again check if we have any NA values, and you can see now ADR has been removed. So it was initially at the one rows we have null values. Now finally we don't have any null values. All the values for the null is 0 here. So in this way we have performed the log transformation in order to handle the outliers. So you can also check for any other attributes. If you find if they have the outliers, you can also perform something called as a log transformation by using this method. So log transformation is a method that will take the value and convert it to log 1 plus that value. I have already shown you right here. It will take that value and perform the log 1 plus that value. So let's say our value is 3, then log will do 1 plus the value 3, and anything that value comes will be our new value, new transformed value. So in our case, if we did, that is log transformation in the case of ADR, if I go back, see here, we did the log transformation for this object ADR. So this was what we did for the log transformation. So whenever we did the log transformation for this, let's say there was 98 values. So ADR values 98 will be taken, and one by one all the values will be taken. So let's say for instance I took these 98 values and I need to perform the log transformation to it. So for this 98 values, okay, I'm taking these 98 values and I need to perform the log transformation. Then what I will do, I will take that 98 values and I will add it to 1 plus that values. That values is 98. So log 1 plus 98. So log of 1 plus 98 is 99. And what will be the log value of 99? And that value will be added in the place of this 98 now. And we will do the same for each and every attributes of this in order to handle the outliers. So this is a one step to handle the outliers. Now in the next video we are going to do next task, which is related to finding the feature importance. I'll see you in the next one.